Let us see how to apply Dijkastra algorithm on a given graph in order to determine the shortest paths. Let us take the example of this graph. A is our source vertex, that is, we want to find out the shortest distance from A to all other vertices in the given graph. We have taken two arrays. Initially, the distance from A to A is 0. This array shows me the current distance from A to that particular vertex. So initially distance from A to A is 0. A to B, the distance is infinite because we have not explored the graph till now. We do not know whether a path exists between A and B or not. Similarly, the distance from A to C is infinite, distance from A to D is infinite, and distance from A to E is infinite. Predecessor list will be marked initially as nil for every vertex. Now what we have to do, out of these values, we see that A is of smallest value. So we will mark A as finalized. The meaning of finalized is that we have determined the shortest distance from A to A, and all other vertices are unfinalized, still to be finalized. Now next step is we will see that whether it is possible by traversing through the outgoing edges from A to determine a shorter path for unfinalized vertices. From A, there are two outgoing edges, A, B and AC. If we follow AB, it means that we have got a path of length 6. See, what we have to do here, we have got a path length of path from A to B will be equal to length of path from A to A. A is finalized vertex plus weight of edge A, B. So it is 0 plus 6, which comes to be 6. This 6 is smaller than infinite. It means we have found a path which is better than the existing path. So what we have to do, we have to update the value, and now the updated value will be 6. Similarly, if we use the edge AC, we have got a better path to C with path length as 4. Let us update the predecessor list also accordingly. So for C, we have marked the predecessor as A, and for B also we have marked the predecessor as A. The reason is that if in the shortest path, predecessor means in the shortest path, which vertex will act as predecessor to the given vertex. So for B, the predecessor is A, and for C, the predecessor is A. So that is why we have updated it, and for all other, it is still to be nil. Now, what we have to do in the second step, in the second iteration basically, again we will find out the value, the vertex with the smallest distance out of unfinalized vertices. We will not, while selecting the shortest value, we will not consider the finalized vertex, or we have to consider only the unfinalized vertices, which are currently B, C, D and E. And out of these unfinalized vertices, the value of the distance for C vertex is smallest. So we will mark C as finalized. Now similarly, again we will find out, as we have found earlier, that by looking over the outgoing edges, whether it is possible to find out a path for the unfinalized vertices, that is B, D and E. So let us see. The outgoing edges are CB, CD, CA. We need not to consider. The reason behind that is A is already finalized vertex. We have to see only for unfinalized vertices. So that is CB and CE. And for C, CB, CD and CE. For B, the existing path is 6. And if we use this CB, so the path will be the length of the path from A to B will be length of path from A to C plus weight of edge C to B. So it comes out to be length of the path from A to C is 4 plus weight of edge is 7. So it comes to be 11. But 11 is greater than 6. It means the newly determined path is not better than the already known path. So we are not going to update this value. So it will be kept as 6 only. Now let us see for others. For D, so length of the path from A to D. So it will be length of the path from A to C plus weight of the edge from C to D. So it is again going to be 11. So now the newly explored path is better than the existing path. Is the length of this path is smaller than the already known path. So we are going to update this value as 11. And accordingly, we have to update the predecessor also. So in the shortest path, the predecessor of D is going to be C. Okay. So this is not going to be updated. This is not going to be updated. This we have marked as nil. And for E, so what we will see, A to E, length of the path from A to C and then C to E. So it's going to be 4 plus 5 and now it is 9. So this is 9. Okay. We are going to update the predecessor also. This predecessor is going to be C. This is 4. It's a finalized vertex. Now, in the next iteration, out of the unfinalized vertices, we see that B carries the smallest value. So we are going to mark B as finalized vertex. And we are going to explore the graph further by looking over the outgoing edges from B in order to determine whether there is a path of smaller length for unfinalized vertices or not. So from B, the outgoing edges are B, E and B, D. We do not look for B, C. It's already finalized. For B, E, now let us see. We have got a path. So length of the path from A to E will be length of path from A to B plus weight of edge B to E. So length of the path from A to B is 6 and weight of the edge is 8. It's going to be 14. So 14 is greater than E. I am not going to update it. It is going to be kept as 9. Predecessor will also not be updated. So it's still 6. Now let us see for D. Length of the path from A to D. It is going to be length of the path from A to B and the weight of the edge B to D. So it's going to be 6 plus 2 is equal to 8. 8 is smaller than the existing path. So it means we have found a path which is better than the existing path. I am going to update it to 8. Others will be kept as they are because they are finalized vertices. And for D, as we have updated the value, I am going to update the predecessor also. The predecessor will be B, and for others it will be same as it was. Now out of these unfinalized vertices, D is of smallest value, so I am marking D as finalized. Let us see whether by following the outgoing edge from D, we get a path for E which is better than existing path or not. So DE is there and length of the path from A to E will be length of path from A to D plus weight of edge D to E. So it is going to be 8 plus 3, 11, which is greater than the already known path. I am not going to update it. This was finalized. So this will be kept as 9. I am not going to update the predecessor also. So this is this one. And in the next step, 9 will be finalized because this is the only vertex left. And in this way, we have finalized all of the vertices. It means that we have found the shortest distance from the source vertex A to all other vertices which are available here. So the final distances from A to A is 0, from A to B is 6, from A to C is 4, A to D is 8, and A to E is 9. And this is the predecessor list. Now I will explain you with the help of example how to determine the path, how to make the path by using the predecessor list. Now let us see from this matrix we know the shortest distance from A to D is 8, but what is the path? So if we want to know the path, so what the approach will be, we want to know the path for D. So the predecessor for D is B. Go in a reverse fashion. The predecessor for B is A and the predecessor for A is nil. So we will stop here. So A, B, D is the shortest path. Similarly, if we want to find out the shortest path to E, the predecessor, you will start from E. The predecessor for E is C and for C it is A. And further for A it is nil, so we will stop here. A, C and E is the shortest path. So I hope the topic is clear to you. Thanks for watching the video. Like it, share it and subscribe for further updates.